Well, in the essence of time, while Jing pulls up the presentation, my name is Stephen Devore. I'm a product architect at Leonardo DRS. So for the past 12 years, I've spent my time designing and, more importantly, making work RF circuits. One of the observations I've made in my time in this industry is while there's a ton of incredibly bright and knowledgeable people, there's a lack of an understanding and appreciating for RF performance. A lot of what we hear about is bandwidth, instantaneous bandwidth, the high sample rates like Roger was talking about today, but not necessarily the performance that goes along with it to ensure that we're getting the signals that we want to see. So today, at least, I want to take a time. I'm going to hold you all hostage, and we're going to go back to school. We're going to learn a little bit about specifications. There'll be a little bit of math, but I'm hoping everyone walks away learning something different. So let's take the guesswork out of some RF specifications. So we're going to go with the who for a little bit from a background. So Leonardo DRS, it's about a $3 billion company, defense contractor. We're listed on NASDAQ now. Probably a lot of us know Leonardo. That's the Italian prime. Leonardo DRS is the US contingent, strict proxy separation from that, under which there's the business unit Airborne and Intelligent Systems. Underneath is Signal Solutions. So this is where I'm from, Frederick, Maryland. We have a brand new state-of-the-art facility built specifically for us. We'll be hosting the VITA meeting in May, so I certainly welcome all of you to come out and see a tour of that facility. There's about 170 of us there, and we're focusing on being the RF provider of choice. So specifically, two things to focus on today. So that's increased dynamic range, we'll talk about what that is, and reducing the spurious. So now why performance matters. Probably seen these charts before. Roger talked about it again. This is a different pictorial way of looking at that. This is the spectrum in Chicago. So everything we deal with in life right now is wireless, whether it be our cell phones, laptops. So the same thing's going to be true on the battlefield. It's an immensely dense spectral environment. So dynamic range is going to be essential. When you looked at that plot, something to think about. So I live in dBs on a daily basis, but not everyone does. 100 dB, that's 10 billion to 1. That is often the difference between the largest and the smallest signal that you're trying to detect at any one time. So we now know that everyone wants dynamic range, but what we found is not everyone understands how to specify it properly, how to test it. So this isn't new. Like I said, we're going back. So our predecessor company, Watkins Johnson, WJ, you might have heard of them, Watergate receiver. They've written on this topic 3 times when they used to publish these tech notes from the 70s and 80s. So these are the individuals, and what I kind of thought about is we're at kind of another generational cusp. So in our industry, those have been standards. I'll go to customers, and one of the graybeards will pull out from their drawer and like, I still have your WJ tech notes. They were written by these guys that are starting to retire. So these have been my mentors. I've had the pleasure of learning from these guys for the past 3 years, because I am by no means an expert. After 10 years, I've not made enough mistakes to really understand RF. But these guys have. So with that, let's talk about some specifications. And unfortunately, there's a lot of them. And while we've made a concerted effort of teaching these and putting them on our data sheets, we'll have 16-page, we'll have 60-page test data sheets. It tends to obfuscate what's really important to the customer. This doesn't mean anything to a user. If you're actually in the battlefield, the IF rejection of a tuner, while important to the designer, doesn't mean anything to the user. So you could look at this from the standpoint of some specs are relatively useless to the user. Others are going to be insufficient. I mean, both are a red car, but clearly very different in their performance. So the capability that's demanded, we're going back to, we want to identify and locate the signals of interest in a congested environment. And so we think we can narrow this down to just 3 basic categories. We have sensitivity. So that's going to be your standoff distance. What's the smallest signal you can detect? How far away from the adversary can you be? Number 2 is going to be the spurious. So this will be your false detects. Number 3 is going to be overload. So in the presence of large signals, how much can you hand before you go blind? So even simpler than that, again, we're going back to basics. There's 2 goals for the radio. It's going to be getting the signals you want and rejecting everything else. That's all the radio's supposed to do. Easy, right? I wish, please. So we'll focus, number 1, sensitivity. That's the first one. That's the simplest one. We're going to start on that with standoff distance. So that's going to be getting the signal you want. And there's this beautiful spectrum here with these nice, strong signals, but our customers inevitably always want that little runt hiding amongst the rest of them. So how do we see that guy? So the key is going to be noise figure. Probably a lot of you are familiar with noise figure. This is a very simple equation for that. So the noise figure, a very definable performance of the radio, your signal-to-noise ratio, 10 log of the bandwidth over the noise floor. That defines your sensitivity. Straight and simple like that. Yeah, I thought it was simple. All right, so typical.
I like digital for that reason.
That's a good point. So typical, I think if we do another survey in here, everyone's going to have their own definition of typical, which is why when you're looking at radios, plots are going to be far more useful. Now, even between these two plots, they could both be set a typical noise figure of 15, which another point that we like to stress in all of our radios is a maximum limit. And that's going to be maximum against all frequencies and all temperatures for operating temperatures. Those are very critical to focus on. Now, you'd be like, all right, I just want the lowest noise figure because that's a direct proportion on your sensitivity. But like much things in life, it's a trade-off. So very low noise figure is going to have a very low dynamic range. You can see the cuff. So you want to tend to be right on that elbow. And notionally, rule of thumb, we're in the 6 to 8 dB territory for a wideband receiver radio. You can go higher or lower, but that's kind of what you're shooting for. So you might ask, but why? So let's look at the minimum detectable signal. So this is the smallest signal above the noise floor that you can detect. And if you had a high signal-to-noise ratio, you might intuitively think that would be easy, and you're correct. And the inverse is going to be true. So if you have a low signal-to-noise ratio, your probability of detection lowers, and the probability of false increases. So if we were to look at that on an equation, this is just a probability chart. So it's saying the ratio of probability of detection versus false alarm relative to your signal-to-noise ratio. All right? So let's say 6 dB. So your signal is 4 times larger than the noise floor. That should be pretty reasonable. Now let's say I want to detect something 90% of the time. So we're looking at that 6 dB vertical line where it intersects with 90%. That means 20% of the time it's going to be a false alarm. I at least wouldn't be the one responsible for sending people or iron into a position that's 20% error. So let's say we want to be less than 1%. That drops your probability of detection with a 6 dB SNR at 50%. So a far more reasonable one is let's look at a 10 dB SNR. And we put that at 90% probability of detection. You're down to 1% less. So now you see the importance of your signal-to-noise ratio in relation to your sensitivity. So how can we improve signal-to-noise ratio? So in general, another rule of thumb, I like to give these out here, is your optimum detection bandwidth is equal to the signal bandwidth. So you can reduce that bandwidth in a couple ways, and it'll improve your signal-to-noise. One is going to be analog filtering, and another, we'll go on the digital side here for Mr. Gipper here, is increasing your FFT size. And you can see it both simultaneously increases your resolution, it's narrowed, while that blue line, your noise floor, is dropped proportionally. So let's look at some empirical data at that. This is a representative radio as an example. So the data here, you can look at this later when the slides are posted to justify the measurements. But the plot, you can see the noise floor is running about minus 108 dBm input equivalent levels. That's measured empirical data. And the analytical calculator in the bottom left from that simple equation I showed here is within a dB. And an analog within a dB is pretty spot on. So we're going to call that a win. Now, if we just did nothing else, no other parameters changed, and we just increased the FFT size, you can see the noise floor has dropped substantially. So your sensitivity has gained, your instantaneous dynamic range, if you will, has increased 30 dB by just computing a finer FFT. So that's digital gain. Now, we talked about the 3 things. We had sensitivity, spurious, and overload. So we'll talk on spurious. Could easily spend an entire day talking about this. I've done many hours of presentations on it. I'm going to talk about one specific spurious, and that's going to be focusing more on those lower levels, which tend to be what we call internally generated. So internally generated spurious are those that are created by the radio in the absence of a live input signal. So you're not looking at an antenna, you're terminated. What does the radio create itself? And if you have large internally generated spurs, it's going to easily mask the signal you can see there on that plot. Worse, if it's on the frequency that you care about, it's going to completely masquerade it. So if we consider the instantaneous spurs, you can very easily, going back to the dynamic range and specifications of a radio, mislead the user. So if I was to put a 1 hertz bandwidth in there, so we showed earlier that with a 50 hertz bandwidth versus a 10 kilohertz resolution bandwidth, we picked up 30 dB. If I did 1 hertz, you would compute your dynamic range at over 140 dB. But that's not real. And there's a couple reasons for that. One, in computing, we're not going to be doing a 1 hertz resolution FFT. It's going to take a second every time to compute that, which in our fast scanning frequency hopper world is not realizable. The second thing is you didn't consider the spurious, the internally generated. So a far more reasonable way to look at this which is talking about that a red car is insufficient for specifying, is stating it within a particular resolution bandwidth. For the signals of interest, we typically care about 10 kilohertz is a realistic way to use that. And it also lands on a reasonable level for internal spurs, both on A to Ds and traditional superhet radios. And you can see that would be a reasonable way to spec that. So I'll touch briefly, and that's something that we could carry on in future discussions, on number 3, the overload. So this is going to be how you tolerate large-scale interferers. So this is your jamming resistance. So we're finally wanting to reject those unwanted signals. So looking on that spectrum, these are the big guys there. No one ever wants the big guys. They're the ones that are always causing the problem, either co-located transmitters or the enemy trying to jam you. So our responsibility as a tuner designer and for our end customers in designing the entire RF chain is not crashing the ADD. That's the easiest thing to do, and it's also the hardest thing to protect from. There are traditional ways of doing that, and that would be in the instance of having a large-scale signal, you just reduce the gain, you increase the attenuation. The problem with that is that's a direct relationship with the noise floor. So we talked about sensitivity earlier. That means you're going to raise that floor, and you're going to mask that small signal. So there's things that ourselves at DRS, we have our proprietary standards on how we match and do this in innovative and novel ways such that we guarantee that full dynamic range without sacrificing that noise floor. But that's a talk for another day. So thank you for your time, and see if we have any questions.